Okay, so let's get started. So we were talking about arrays at the last class. So remember, in arrays in C, there's no bounds checking, right? So unlike Java or Python, if you index into C doesn't care how you index into an array. It will happily try to index into the array using whatever index you provide, right? So in other words, it doesn't check the index and throw an exception or something like that. It just indexes into the array. Right, so remember that if you use an invalid index, then if you're lucky, the program crashes. Right? And if you're unlucky, the program keeps on running, but something has probably gone wrong, and you have to figure out later on what has gone wrong. Right? So here's this. There was this one program here that I showed you. We have a string. We have an array of characters. Right? Its length is 1, 2, 3, 4, 5, 6, 7. Now remember, there's an extra /0 on the end. Right? So the length of that array is actually 8. Right? And if you write, so if I take the address of the first element of the array, right? Again, so remember, arrays and pointers are basically the same thing. Right? There's a duality between an array and a pointer. Right? The pointer is just the address of the pointer points to the first element of the array. Right? And if I add 100,000 to that pointer. So in other words, if I try to access the 100,000th element, 0, 1, I guess 100,001th element of that array, right, and set that value to the question mark, right, when you run that, this one's array 6, right, your program just crashes. Right? Now, if you're unlucky, right, so here's another program. This time I'm going to overwrite the 9th element of that array. Right? Now remember, this array only has 8 elements in it, right? So there's 7 here plus the /0, right, to end the string. So there's I'm going to go 1 past the end of that array, right? And if you do that, right, the program runs. So no error or exception is given back to the user, right? And the value that was stored after the array happens to get overwritten, right? So x is no longer 100. X got overwritten and is now 63, right? Because I print out the array here, and then I print out the value of x here, right? And x is 100, but I never changed x anywhere in the program, right? But when you print it out, x is now magically 63. So you have to be very careful when you index into an array, right? It's always the programmer's responsibility to make sure that they're indexing correctly. Okay, you can create what are called multidimensional arrays in C, right? So you can create what are rectangular multidimensional arrays, right? This is a little bit different than Java. So in Java, you can create non-rectangular multidimensional arrays. In C, you have to create rectangular ones, unless, well, I'll leave it for that for now. Right? So for example, if I want the matrix that has 2 rows and 3 columns, right, then I can write that as an array of arrays. Right? So down here. Right? So the elements here, 0, 0, 0, 1, 0, 2, those are the indexes for each element of the array. Right? So the 10, you'd use indexes 0 and 0. To get the 11, you'd use indexes 0 and 1. To get the 12, you'd use indexes 0 and 2. Right? So these are similar to how a mathematician would write the indexes for a matrix. Right? Now notice this thing here. It's a 2-dimensional array. So what it really is, it's an array. Right? So that's why I have one set of braces. Right? But inside the braces, we have nested arrays. Right? So in fact, you have 2 arrays inside of another array. Right? So this thing A is an array of 2 arrays. Right? Each one of those arrays has 3 elements. Right? So you have an array of arrays. Right. So the element A0, right? So the element A0 is that first array here. Right? So it's the array containing the 10, 11, and 12. Right? And then the element A1 is another array, right? And it's the array containing the elements 13, 14, and 15. Right? So A23 gives you a multidimensional array of 2 arrays, each having 3 elements. All right, so there's my 2 arrays. There's my multidimensional array on line 1. right, I'm going to loop from 0 to 1. Right? So in other words, I'm going to loop over the two arrays that are inside of A. Right? Each loop iteration, I'm going to go from 0 to 3, so 3 elements in each array. Right? So I'm going to loop over the elements of each individual array using the J loop. Right? And then I'm going to print them out, putting a tab after each element. Right? So I'm going to print out the elements 10, 11, and 12. Right? Then I'm going to print a new line. I'm going to go back up to the for I loop. Right? And that'll take me to the second array. And then I'm going to print out 13, 14, and 15, and then print a new line. That's array 8. Right? And so when you print that out, you get 10, 11, 12, 13, 14, 15. Right? You're just printing out the two arrays. Okay, now there's something funny about C arrays, C multidimensional arrays. The language standard says that if you have a multidimensional array, all the elements must be stored contiguously in memory. So contiguously means sequentially, right? So there's no, the elements can be stored one after the other, right? And so what does that mean? So for this array 10, for that array 10, 11, 12, 13, 14, 15, right? If you imagine that your memory is just a big table, right, where you've got rows, right, and each row can hold one value, right? The standard says that that array must be stored like this, right? So it must be stored like that. And so what does that mean? Well, that means if I get a pointer to say the first element of the array, right, I can get to the second element of the array by, so if I have star p, points there, right, then p1 points there, p2 points there, and so on, and so on, and so forth. Right? So even though it's a multidimensional array, you can still use what looks like to be a regular pointer to get to each element of the array. Right? So in other words, you can treat this multidimensional array as though it was just a one-dimensional array. Right? Now, C happens to use what's called row major order to store the elements. Right? That means it stores the elements of the first array like this, and then it stores the elements of the second array. Right? There are elements that do this, there are languages that do this differently. So there are languages that use column major order. So they will store, so this is C. There's another language out there called Fortran, which is about as old as C or slightly older. That stores the elements 10, 13, 11, 14, and then 12 and 15. Right? So Fortran is column major order. Right? And C is row major order. Anybody in here use MATLAB before? MATLAB, good. MATLAB's column major order, which is very confusing if you're trying to switch between MATLAB and C. Right? MATLAB actually uses Fortran underneath, which is why it works that way. So you can write a little program like that, right? So I can create a pointer that points to the first element of the array, right? Now remember that array is A, right? The name of the multidimensional array is A, right? But I need the first element, so that's A00. Right? And I can take the address of that first element, right? And that gives me a plain old pointer to int, right? That points to the first element of that array, right? And then I can access the elements as though it were a one-dimensional array, right? Just like that. So this is commonly used in computer graphics, right? So in computer graphics, you've got three-dimensional points, right? So you have triplets of numbers. Right? And often the arrays are just laid out flat in memory. So you have x, y, z for point 1, and then x, y, z for point 2, and then x, y, z for point 3, and so on, and so on, and so on. Yeah?
Do you have to specify the sizes in C?
Do I have to specify the sizes? Yes. So you mean here, the 2 and the 3? Okay, so if you have an initializer, the answer is no, right? So I can write, is that true? I don't remember if you have to, you know what, let's try it. It could be the case that you need one of the initializers, but let's see what happens. Sorry, you may need one of the dimensions. But we can try, so that's 8, right? Let's see what the compiler says. No, it doesn't like it. So it says when you declare A as a multidimensional array, you must have the bounds for all dimensions except the first. Okay, so that means this says that you need a 3 here. Okay, and now it's happy. There we go. Yeah.
Does that mean that you can add as many like arrays into that like whole array?
No, so
You have, like,
that means, where's my program? Okay. So does that mean you can add as many more? Yes. So the answer is yes, right? So I can put in another one here. But you can only do this in the initializer, right? So if you're initializing like this, then the answer is yes, right? And so now, well, wait, I have to change the loop, right? J is 3 here. So now I have 3. Oops. So yeah, that works. But only in the initializer, right? Yeah. Right, okay, so you can actually treat a multidimensional array as though it were just a flat one-dimensional array, right? And it's sometimes useful to do. Okay, so for the time being, that's all I want to say about arrays. There's something pretty important that's missing. There's 2 things that are missing so far. So number 1, all of the arrays we've created so far, they have a constant number of elements, right? So in other words, there's always a number or numbers in here. Right? C99 has what's called a variable-sized array. So instead of a number, instead of a constant, you're allowed to use a variable as the number of elements in the array. Right? So that's a new addition to the language for C99. Right? Prior to the standard C99, you did not have variable length arrays. The other thing that's missing here is how do you create an array that you can actually return back to the caller? So in a function, can you make an array and return it back to the caller? Right? If you do what we've been doing so far, so you make int a3, and then you try to return the array back to the caller, bad things will happen. Right? You can try it if you want to, if you have some free time. So there's still one more thing that we have to do, and I have to show you how to allocate a new array. Right? Well, that's going to be next week. All right, and we're not done. Okay, so for the time being, I just want to move on to the types, talking about the arithmetic types. Okay, so this was actually 2 lectures ago, right? So I told you, you know what a type is, right? Set of values, it's what you can do with the values, right? And I pointed you to this link here. I didn't have Wi-Fi, so I couldn't actually show you that page. But I do want to talk about that page because it's fairly important. So that's that page right here. So it's the page that describes the arithmetic types in C. Right? Now, you know in Java, right, Java's got some primitive types. Right? This has got byte, short, char, int, and long. Right? And Java says that all of those values have very specific sizes. Right? In other words, they all take up a certain amount of memory. C has slightly different types. Okay, so it has char, right, which is right there, right? But it's also got this thing unsigned char and signed char, right? So it has, for all the integer types, it has unsigned versions of the types, right? So those are types, those are values that start at 0 and go up to some maximum value, right? The signed types, there's some negative, some minimum negative value, and then some largest positive value that they go up to. Right? So for all the integer types, you've got the signed and unsigned variants. And so C introduces short int, unsigned short int, right? So the two versions of short int, right? You have int, which is the same as signed int, right? And you have unsigned int. And then you've got long int, which is also long, right? And then you've got unsigned long int, right? Which is also unsigned long, right? Another wacky thing in C is that C doesn't care what order you put these words in, right? So unsigned long int is the same as long int unsigned long, right? Which is crazy, but that's just the way it is, right? So that's why that slide says make sure you use the middle column when you use a type, right? So if you want a short int, right? If you want a signed short value, use the words short int. Right? If you want an unsigned short value, use the words unsigned short int. Right? And if you want an int, if you want a signed int, use int. If you want an unsigned int, use unsigned int. Yep.
Scroll up, it says that int is the most optimal type. It's a little bit higher.
Right here.
This is the most optimal interval type.
Yep.
What does it mean to be the most optimal?
Okay, so what does it mean to be, that's a good question. What does it mean to be the most optimal? So the way, you haven't taken the architecture course yet, right? Okay. So the way your computer, so the way most modern CPUs work is that there's something called the native word size, right? So most of your CPUs are probably 64-bit CPUs, right? That means it wants to manipulate information that's 64 bits long, right? So if you're passing around an int that's 32 bits, right? It can't just pass around one int, it's got to pass around an int and something else, right? The something else may be junk, but it doesn't matter, right? Now, also part of your architecture is your CPU has circuitry on it that's designed for different sized quantities, right? So here it's trying to tell you that int is supposed to be the one that's optimized for your particular architecture, right? Most desktop CPUs are optimized for 32-bit integer operations, right? It's just the way that the hardware is built, right? Not all hardware is built that way, right? So embedded systems, they might have 8-bit or 16-bit ints, right, that they can use, right? And so it changes depending on your architecture. So that's what it's trying to tell you there. The int is the one that you want to use for the fastest integer performance. And even that's not necessarily true in modern architectures, right? So in modern architectures, long might just be as fast as int because it wants to pass around 64 bits anyway instead of 32. Okay, now, Java says that a short is 8 bits, right? C says it must be at least 16, and it doesn't say what it should be. It just says it has to be at least 16, right? Sure, wait, in Java, short is 16. Right, sorry, byte is 8 in Java, right? So C does not mandate the actual size. It just says it has to be at least something, right? So short, char is actually the shortest, is the smallest integer type that you can have, right? So char is usually 8 bits, but that's not guaranteed, right? Short is at least 16, right? So short's supposed to be bigger than a char. Now int is supposed to be bigger than short, right? Well, not exactly, right? It has to be at least as big as short, right? So that's why it says at least 16 here, right? And then long says that it must be at least 32, right? And then long says it has to be at least 64, right? So C doesn't actually mandate the size, it mandates the ordering of the sizes, right? Now these other columns here are trying to tell you what the most common sizes are, what the sizes are on the most common architectures that are out there. LP32 is Windows 32. ILP32 is Linux 32-bit. LP64 is Windows 64. LP64 is Linux, I think. Somewhere it's written, oh, here it is. Yes, I got that right. Right, so on the most widely used desktop architectures, these sizes are actually fixed, right? But that's not guaranteed to stay the same in the future, right? They could change, right? So you can see on the most widely used architectures, right? The size of an int is 32, right? That matches Java's definition of how big an int should be, right? A long, interestingly enough, on Windows is 32 bits, right? Whereas on Linux it's 64, right? Java says it should be 64, right? And then, so Java doesn't have a long, right? But C says if you have a long, then it has to be at least 64 bits, right? And you can see here that on the most common architectures, in fact, they are 64 bits. So this thing down here, that line right there, is all that C specifies, right? It says that the size of a car must be 1. Size of short has to be at least as big as car. Size of int has to be at least as big as short. Size of long has to be at least as big as int, right? So if you're programming something and you're assuming that some value has a certain number of bits, your program is not going to be portable, right? It'll work on whatever system you're targeting, but as soon as you try to compile that for some other architecture, it may not work. So that's what you have to watch out for in C. It used to be a huge problem in the mid-90s because there were lots of different architectures that were commonly used at that time, right? There's 16, 32, and 64-bit platforms were all widely used. So someone would write a program on their Sun workstation and they take it to a Windows machine and it wouldn't work anymore. So that's you have to watch out for that. Okay, the floating point types are less confusing, right? So floating point types more or less correspond to the Java floating point types, right? Float is single precision floating point, if it's supported, right? If it's supported on your architecture. So float in C is the same as a float in Java for the most part, right? A double in C is the same as a double in Java for the most part, right? Now C also says that there should be a long double, right? So long double does not exist in Java, right? But there is a standard for it, right? So it's the 128-bit standard for the 128-bit floating point standard, if supported, right? And it actually tells you, right? So here it tells you that format is supported on those platforms, right? HP-UX is Hewlett-Packard Unix. Spark is Sun Unix, which no longer exists. MIPS is, I can't remember, not widely used though. ARM64, I believe, is your Mac, your new Macs. ZOS, I don't know what that is. And it tells you that, so Intel and AMD, they don't have, or they don't natively support binary 128. So there's no long double on most Windows or Linux machines. Okay, good. Right. Okay, so if you need to know what are the actual limits of your numbers, right? So what's the minimum value, what's the maximum value? You just look in this header file called limits.h, right? If you hit that link, it'll take you to the web page where you can find all the constants that are defined in that header file, right? This just repeats what I just said, right? So the C standard only imposes 3 constraints on the integer types, right? So everything is a integer multiple of car. All the sizes are integer multiples of car, right? Each integer must support a minimum range of values, and smaller types cannot be wider than larger types, right? So a car can't be bigger than an int on your computer. All right. So one of the big differences between C and Java is that C has unsigned values, right? So unsigned values have ranges that start at 0, right? And their maximum value is greater than the corresponding signed type, right? So the largest unsigned int is bigger than the largest signed int, right? And so the question is why? And the answer is because you need 1 bit to store the sign on a signed value, right? You need a bit to store whether it's signed, so you need something to say if the quantity is positive or negative, right? In the binary number system, that eats up 1 bit, right? So on a signed value, you lose 1 bit. Right? Now, unsigned values, they have the simplest binary representation, right? So that's an 8-bit unsigned an 8-bit unsigned binary number, right? Which on most computers would be an unsigned car. Okay. Now the way the binary number system works, right? The rightmost number, right, is either a 0 or a 1. You just multiply that by 2 to the power 0, right? The second number from the right, you multiply by 2 to the 1, right? The third number from the right, you multiply by 2 to the 2, and so on, right? So in an 8-bit number, you multiply that number by 2 to the power 7, right? And your numbers are just 0 and 1, right? Because it's binary. Right, so the number 0, 1, 1, 0, 1, 0, 1, 1, right? Well, there's a 1 there, so 1 times 2 to the 0 is 1, right? There's a 1 here, so 1 times 2 to the 1 is 2, right? There's a 0 there, so it's just a 0, right? 1 here, 1 times 2 to the 3 is 8, right? There's a 0 here, so it's just a 0. 1 here, 1 times 2 to the 5 is 32, 1 times 2 to the 6 is 64, and 0 is a 0 here, right? And then you just add them all up. Right? So when you add these all up, you get 107. Right? So that's the basic binary, that's the most basic binary number representation that you can have. Right? Okay, now the C standard has no way to specify binary numbers. Right? So there's no way for you to write a sequence of zeros and ones in C in a standard portable way. The compiler that we're using in this course, so GCC and CLang, I believe, also supports this. So if you're on a Mac, this should also work, but I haven't checked it yet. Right? There is an extension specifically for this purpose, right? Because sometimes it's really useful to work in binary. Right? So to write a binary number in GCC, you can write 0b in front of your bits. Right? So 0b, 0, 1, 1, 0, 1, 0, 1, 1, is that binary number right there. And you can print that thing out as either a char, right? So remember, it is an unsigned char, so I am allowed to print it out using the char conversion, right? So that's %c, right? Or I can print it out as a number, right? %u. Remember, this is a char, so it's supposed to represent some sort of character, right? So you can use either one of these, but you get a different result depending on which one you use, right? So let's see what happens when you run this. Okay, so this is, what is this? This is ucar. Okay, so remember, I'm going to print out that binary number, right, as a decimal value here and as a character here. Okay, so apparently it's the character k, right, and apparently it's the number 107, right? Well, we already knew it was the number 107, so that's not surprising, right? But when you print it out using its character representation, you get the letter K, right? That just corresponds to the ASCII number code for 107. Yep.
Is unsigned U? That's like the unsigned.
Unsigned, yeah, unsigned. It turns out in this case it doesn't matter if you use U, D, or I. You'll get the same value either way. So D is decimal. D is integer. D and I are integer. You'll get the same answer. Yep.
When you want to do an unsigned long, though, you have to do UL.
Yep.
So why don't you do U, or is that just kind of the way it is?
No, it's just a way. So if you look up the table, U is for any non-long value, any integer value, any unsigned integer value. Yep. Okay. For an n-bit unsigned binary number, right? So for example, for an 8-bit unsigned binary number, the maximum value is 2 to the n minus 1, right? So that'll be 255. 255 for an 8-bit number, right? And this is easy proof by induction if you wanted to do it. I'm not going to do it. I'm not going to ask you to do it, right? If you want to prove this, it's easy to do, right? So the proof by induction is you just check for n equals 1, right? And then you use the induction, and then you assert the induction hypothesis and go from there, right? The proof's straightforward. Okay, so it's 255 for an 8-bit number. Okay, now what about the signed numbers, right? So the signed numbers have ranges that have a most negative value and a most positive value, right? So it's similar to the Java int and long, right? You need 1 bit to indicate if the number is negative, right? So that's why, so you lose 1 of your bits for the sign. Now, here's the other crazy thing in C. The standard does not say how your signed numbers are represented. Right? It doesn't say what their binary representation is. Right? Now, in current architectures today, almost all of them use what's called 2's complement, right? And in the future, so sometime, some version of C20X, so 2x, sometime in the 20s, the standard is supposed to say that it will only support 2's complement, right? But there are other ways of representing signed numbers, right? So one of the ways of representing signed numbers is with one bit dedicated to the sign, and then the remaining bits dedicated to the value. And then there's something called 1's complement, right? Where there's one bit that can be either the sign or value. 2's complement, one of the bits is either the sign plus a value or 0. Okay, so in 2's complement, we lose, well, we don't lose the leftmost bit. The leftmost bit has a certain interpretation. Okay, so the leftmost bit, if it's 0, then the value is just 0. Okay, so 0 is just 0. If the binary value is 0, then the value of that, then the weight of this number is just 0. If it's 1, then the weight of that value is minus 1 times 2 to the 7. Right? So it's minus 1 times 2 to the n minus 1. Right? So in this number here, where there's a 1 in the front, that bit ends up contributing minus 128 to the final value. Okay? So minus 128 to the final value. And the rest of it works the same. Right? So if you sum all these up, you end up with minus 21 in this case. Right? So that's how you get a negative number in 2's complement. Right? The first bit's always 1 if it's negative. Right? And the weight of that first bit is minus 2 to the n minus 1. All right? Okay, now you can figure out what the 2's complement representation of minus x is. Right? So if I have a value x, I can compute minus x just by flipping the bits and adding 1. Right? So what does that look like? So here's the number 1. Right? 0, 0, 0, 0, 0, 1. Right? There's your binary number 1. If I want to figure out what is minus 1 in this representation, right? You flip all the bits. Right? So if there's a 0, you get a 1. Right? 0, right? 0, 1, 0, 1, 0, 1. If there's a 1, you get a 0. So you just negate all the bits. Right? And then you add 1 to that number. So I'm going to add 1 to the number 1, 1, 1, 1, 1, 1, 0. Right? So if I put a little 1 here, 0 and 1 is 1. Right? And then I'm going to do 1 and 0, 1 and 0, 1 and 0, 1 and 0, and so on. Right? So the value of minus 1 in 2's complement is the binary number whose all the bits are 1. Right? And you can check that by actually evaluating the result. Right? So remember, this bit here, it's 1, so it has a value minus 128. And then all of the other ones have the value 2 to the n minus whatever. Right? So 2 to the 6 is 64, 2 to the 5 is 32, all the way down to 2 to the 0, which is 1. Sum them all up, you get minus 1. Right? Here's the number 56. Right? So flip all the bits, you get 1, 1, 0, 0, 0, 1, 1, 1. I should do this on the chalkboard. Okay, so I've got 0, 0, 1, 1, 1. 0, 0, 0. Okay, I'm going to flip all the bits. So I get 1, 1, 0, 0, 0, 1, 1, 1. Okay, now I'm going to add 1. Right? So this is just like addition with decimal numbers, except now you're using binary numbers. Right? 1 plus 1 is 0. Carry the 1. 1 plus 1 plus 0 is 0. Carry the 1. 1 plus 1 plus 0 is 0. Carry the 1. 1 plus 0 is 1. 0, 0, 1, 1. Right? And so there's your 2's complement. Right? So it's, sorry, you probably can't see that down there if you're up there. But it's right here. Right? And so when you compute that value, right, minus 128, there's a 64 here, There's an 8 here. Add that all together, you get minus 56. Right? And this works for negative numbers too. So if I start with minus 56, flip all the bits, and then add 1. Right? So remember, when you add 1, you're going to get 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. There's your 1. And then 1 and 0, 1 and 0, 0 and 0. Right? Add them all together, you get 56. Okay. Now there's something funny about the 2's complements representation. Right? And you saw this in CISC220 Right? The range of values is asymmetric around 0. Right? So for any n-bit number, the range of values is minus 2 to the n minus 1. Right? So for an 8-bit number, that's going to be minus 127. Sorry, not 127. Minus 128. Right? Up to, right, 2 to the n minus 1, minus 1. Right? So up to 127. Right? You lose one number because 0 isn't signed. Right? So 0 you count to the right-hand side of the range, and then the rest of all the negative numbers are on the left-hand side of the range. Right? But that means you have a problem. Right? Your signed integers are susceptible to a very, very hard to find error. Right? If I negate that, right, there's no 128 in this representation. So minus x doesn't always exist. Right? Similarly, if I take the absolute value of that, well, minus 128 doesn't exist. So that might not work either. Right? If you multiply by minus 1, right, again, that quantity may not exist. And if you divide by minus 1 or take the remainder with minus 1, that value may not exist. Right? The C standard doesn't say what happens if you try to do one of these things. Right? The C standard says this is undefined behavior. So if you try to negate minus 128 with a signed char, right, the compiler can do whatever it wants. Right? Now, what exactly does it do? Well, it depends. It depends on your compiler. Right? So this is called 2's. Oh, that's not right. That's the binary representation of your program. 2's C. There we go. Okay. So 2's, I'm going to take, so S char min, that's signed character, that's the minimum value for signed characters. Right? So it's minus 128. Right? I'm going to print the value. Then I'm going to compute minus C. Right? I'm going to see what happens. I'm going to take the absolute value of C. I'm going to multiply C by minus 1, and I'm going to divide C by minus 1. Right? And let's see what happens. Well, first of all, let's see if this compiles. 2's. Oh, whoa. Okay, so as far as the compiler is concerned, this is all fine. Right? It's all syntactically find C. When you run it, you get minus 128 for all the values. Right? So the smallest signed char is minus 128. Apparently, the negative of that value is also minus 128. Right? The absolute value of that value is also minus 128. Right? Multiplying it by 1 gives you minus 128. And dividing by minus 1 also gives you minus 128 on my compiler on this computer, compiled the way I just did it. Right? If you change the way you compile it, you might get different results. If you run it on a different computer, you might get different results. If you use a different compiler, you might get different results. Right? So you have to be very careful about this problem here. Okay, so S char min, that comes from limits.h. Right? So that's where you find that value. Absolute value. So you might think that the absolute value function would live in a math library somewhere. Oddly enough, it doesn't. It lives in the library called standard lib. Right? So if you want to take the absolute value of an integer value, you have to include standard lib, right? Which is sort of confusing. All right, now what about the floating point types? So I don't have to say much about the floating point types because they behave pretty much the same they behave in Java. Right? The only thing you need to know about is if you want to find the smallest and largest, if you want to find the largest floating point value, or if you want to find the smallest value that's bigger than 0, you look in limits.h. Right? If you happen to need infinity or nan, so not a number, then you have to include math.h. Right? And finally, math.h is where you want to look for most of the standard library mathematical functions. Right? So math.h is similar to java.lang.math. Right? Except for abs, which for some weird reason is defined in standard lib, and I don't know the reason why. Right? If you hit that link, you will find the documentation for all of the math functions that are available to you in C. Okay, here's a little program that uses some of the math, that includes the math library. Oh, sorry, hang on. Right, that includes the math library, and then calls the math functions. Right, so there's your square root. Right, there's pow, or exponentiation. Right, so that's x to the power 2. There's max for floating point numbers. So for doubles, the function is called fmax. Right, for ints, the function is called max. Right, now remember, C doesn't have you cannot overload a function in C. Right? In other words, no two C functions can have the same name in the same program. So all of the function names are slightly different than what they look like in Java. Right? In Java, you've got a bunch of max functions that all have the same name. They take in different types. In C, they all have slightly different names. Right? So you'll find an fmax, a max for ints, an lmax for longs, and something else for doubles, or something, or for other values. You can look in the documentation to find out what the correct function is. Okay, now when you go to compile this program, you have to do something slightly different than what I've been showing you. Okay, so if I just do what I've been showing you so far, right? So I think normally we've been doing something like standard C99, right? And then we put in the name of the file that you want to compile. And then you put in -o and the name of the executable program. If you do this, you'll get an error, right? You'll see something like user bin ld, in function main. There's an undefined reference to pow, right? And then you'll see collect to error ld returned 1 exit status. Okay, so what does all that mean? ld is called the linker, right? So I'll explain what that does in a second. To make this error go away, well, first of all, what the error is complaining about is it doesn't know where to find the pow function, right? More specifically, it does not know where to find the implementation of the pow function, right? So you have to tell you have to tell GCC where should it look for this function called pow, right? The implementation. So the function called pow is defined inside of a library file called math, right? It's actually called libmath, right? So you need to put in the flag -lm. Right? Sorry, it's actually called libm, not libmath. It's actually called libm, right? So you have to put in the flag -lm to tell the linker link to the math library called m, or link to the library called m, right? And then when you do that, everything's fine. And then you can run your program, right? So when you run your program, you get 1.4214, right? 2 and 5.7, right? Square root of 2, x to the power 2, right? So x is the square root of 2, so x squared is just 2, right? And then the max of 1.2 and 5.7. Okay, so how did I print those out? Right, so I'm printing them out using LF, right? So F is floating point, L is for doubles, right? When you use the F or LF conversion specifier, right, what you end up with is you always end up with 6 digits to the right of the decimal place, right? That's why it looks the way it does, right? So notice that there's always 6 digits after the decimal point. So the default precision is 6 digits, and you can change that if you want to, right? So the way to change that is you write dot, so the period, followed by some integer value, right? And that goes before the F, right? So it's percent dot some number LF or F, right? Where that's the desired precision, so the number of digits after the decimal point. So for example, I can write dot 12F, and that will give me 12 digits after the decimal place. I can write dot 2F, and that'll give me 2 digits after the decimal place. And I can write dot 1F, and that'll give me 1 digit after the decimal place. So that's math demo 2, and there's the output there. All right? So if you want to specify the number of digits after the decimal point, use dot number of digits. This is funny. If you don't specify enough digits, sometimes it matters, right? So for example, if you have a value that's the cosine or the sine of an angle, then the number of digits after the decimal point can really affect what happens when you convert that value back to the angle, right? Depending on where you are in the range of, depending on what the value is that you've taken the sine or cosine of the angle of, right? If you just dump out the format with 6 digits, you can lose 2 or 3 degrees worth of precision when you convert the number back to a decimal. There's a tracking system that I use for research that dumps out the output to 6 digits. And so for certain angles of your object, the angle that it reports that the object's at is completely wrong. And that's because they only printed out 6 digits. So you have to be a little bit careful about this too. Right? Yes?
What happens if you put like, 30?
Yeah, what happens? That's a good question. Does it work? The answer is yes, it works. You can put like 120, you'll get 120 digits. Most of them will be 0.
Okay.
Yeah. But yeah, it works. At least it works on my compiler on my computer. I don't know if it works on every compiler. Yeah. But yeah, it works. I don't think the standard says anything about the number, the conversion number. I've never seen it anyway. All right. So this is what the L flag means. So when you compile a C source code file, what actually happens is you produce what's called an object file, right? And that's just made up of machine code. So that's the language that your CPU can, well, your operating system can understand, right? Now, if your source code file contains a function call to some function that's not defined in the file you just compiled, then a program called the linker links the object file to the other object file that contains the function definition or to the library file that contains the function definition, right? So -L followed by a library name tells the linker to link to that particular library file, right? M indicates the standard math library. So -LM says link to the math library for any of the math functions, right? And so that's why you need the -LM flag when you compile that math program. All right, that's it for today. Oh, you guys know the assignment's out, right? Yes, everybody knows? Okay. It's fairly short.